this is the second half of 17.4, Green's theorem. In the first half, we talked about the circulation of a vector field around a closed curve, and how you can compute that circulation, which is a line integral, by doing a double integral of the curl. The flux form of Green's theorem is similar in that it tells you how to do a line integral by doing a double integral instead, but this time, instead of circulation, we're talking about flux. We introduced what the flux integral was very briefly, like earlier in the chapter, but let's just figure out why the flux integral is written this way and why it equals this again. So let's say you have a closed curve, C, and at each point you can imagine a normal vector that's pointing outward. Somewhere n is the outward normal vector. So like at this point, the normal vector would point this way. At this point, normal vector would point this way. Everywhere you go around the curve, normal vector tells you which way is out of the region that you're walking around. F dot n asks, how much does the vector field agree with n? So in other words, how much does the vector field point out of the region? Instead of thinking of the curve C as like a path that we're walking around and the vector field as like the wind, instead it's better in the flux form to think of the path as like a fence that's trying to keep stuff inside. And the vector field is some force that's trying to push stuff out of the fence or push it, like jam it in through a membrane or something. If F and N have a lot in common, that means that the vector field is pushing stuff outside of C. That would be a positive flux. Okay, how does F dot n ds turn into this thing? Well, the key is that if, like we know what dr was from before. Dr was dx dy. And dr is like a little tiny vector that points in the direction that the curve is going. So like here, dr would point this way. N has to be orthogonal to that. So nds is going to be made of the same kinds of things, but it's going to have like a dy in this slot and a dx in this slot, so that when I dot these, I can cancel them. Now I need to make one of these negative, and I can never remember which one, but one of these has to be negative so that when I dot them, one of the terms is dx dy, and the other one is minus dy dx dy, so they cancel. One of the minus signs makes an outward normal vector, and one of them makes an inward normal vector, and I just can never remember. So let's see if we can figure it out. Here, the dr goes straight to the left, so it has a dx is negative, but the normal vector goes up. So the y component of the normal vector is positive. So I believe that means we want to put the minus sign here so that the y component of the normal vector is the opposite of the x component of dr. I think that should work. Let's make sure that it works. Here I'm going down, so I have dy is negative, and then I end up going to the left in nds. Yes, that works. Okay, so what happens if you do f dot nds? F dot nds is just fg dotted with this thing, dy minus dx. So I get f dy minus g dx, which is this right here. Now, Green's theorem in the flux form says that actually you can do this line integral by doing a double integral over the region on the inside instead. And we spent a bunch of time doing the proof last time for like certain shaped regions. And the outline of the proof is basically you like deal with this part first, and it corresponds to this part. And then you do this double integral, and it ends up being equal to this line integral. So I'm not going to show you that part of the proof again. It's just, this is another form of Green's theorem, and the proof is basically the same. I'm not sure what's going on with this picture, so we're just going to skip it. But that thing on the inside of the double integral this time, which was partial f partial x plus partial g partial y, that's different from what we were integrating in the circulation form of Green's theorem. The thing we did in the circulation form was called the curl. The thing we're doing here is called the divergence. Let me flip to the thing that's going to be our summary at the end of the class. it has that. This means we've finally, for the first time, actually heard all the words that are in this this thing that's up above me. It's got grad, which is the gradient, the curl, which was in the circulation form of Green's theorem, and the divergence, which is this operation right here. Yeah, so somehow if you can figure out what the gradient, the curl, and the divergence are all about, then you've got most of vector calculus all like lined up. Okay, there's a word for this. If the divergence is 0, then we say that the vector field is source-free. Curl, I had an intuitive explanation for what the curl was. It was like how swirly the vector field was. The divergence is kind of like how explodey the vector field is. Oh dear. Okay, so say you go around this curve and you want to know whether there's any flux through the curve. The way that you would get flux would be if the vector field was like pointing outward mostly. The integral will allow for sometimes the vector field to be pointing out and sometimes for it to be pointing in. But if your vector field is like exploding, then you'll have positive divergence. That's very oversimplified, but that's what the divergence tries to measure. Is like, is there a source? Is it like whoosh, like pushing outward? If so, then your double integral will show you that you'll have a bunch of flux through the curve. Okay, let's do some. So here we're going to have a source. So the divergence will not be 0. Notice that in the picture here, the arrows are all kind of like exploding outward from the source. We'll say that the velocity of the water is modeled by this vector field in meters per second. So these arrows, they're not like wind or gravity, they're velocity vectors of the water. Okay, say you put up this rectangular box and it's made of like a mesh or a membrane or something. How much water is going to flow through that membrane? Well, you could actually do this by doing 4 line integrals of f dot n ds. It would be kind of painful, right? I think so. So let's just see what that would look like. This is the definition of what the flux is through these things. You would have to parameterize all 4 curves. That's probably the worst part. Then f. Oh yeah, it's like pretty gross. Okay, so Green's theorem will get us out of this. Excuse me. Green's theorem will get us out of this. So the integral of f dot n ds, due to Green's theorem's flux form, we can just do the double integral on the region of the divergence of the vector field. This says you want to know the flux through a curve. Instead, just go inside the curve and add up all the explodiness. Add up all the divergence inside the region. Well, partial f, partial x, and partial g, partial y. Here's f, and here's g. Partial f, partial x is 5, and partial g, partial y is 3. So I can take the 5 plus 3, that's 8. I can factor the 8 out of the integral. And I don't end up even having to do the integral, because the double integral of dA is called A. It's the area of the rectangle. The area of this rectangle is, well, its width is 2, and its height is... What's going on here? This y-coordinate can't be minus 3. I guess this y-coordinate is supposed to be plus 3. So its width is 2 and its height is 5. So its area is 10. So let's try to get the units worked out here. What did we actually end up with? So I had meters per second. F was in meters per second, and G was in meters per second. when I take the x partial derivative of f, x is in meters. So I'm like, when I take the derivative with respect to meters, I end up dividing by meters. So partial f partial x loses its meters. Partial g partial y, also I take meters per second divided by meters, and I get 1 over seconds. All of this added together then is in 1 over seconds, and dA is an area, it's in square meters. So the final answer is 1 over seconds times square meters, which is square meters per second. Find the amount of water per second that flows across the rectangle. I got an answer in square meters per second. I guess the problem is that it didn't tell me how deep the water is, so I didn't end up with cubic meters. So this is my answer. It says, hey, if you told me how deep the water was, like if the water was 3 meters deep, then I could tell you the volume of water that goes through. But as is, I just can tell you how much of the surface of the water passes through, which is kind of cool. So if this was 3 meters deep, then you would multiply by 3 meters and you'd get a cubic meters per second. But just make sure that the units come out to something reasonable. Nice. Okay. This is... So this is a clever trick that people use Green's theorem for sometimes. We're talking about a... You should write a circle here when you're asking this question. So the question that we're asking here is, suppose that you are doing this particular integral, which is like, I don't know, why are you doing this integral? But let's just suppose you are. And you know that the curve is the boundary of a region. What happens when you do this integral? Well, here's what this is it looks like the flux form of Green's theorem. Let's go get it. It's got an f dy minus g dx, I think. F dy, so here's f is x, minus g dx, where g is y. So this integral whatever this thing is the integral of f dot n ds. It's a flux integral with a weird 1/2, where f is x comma y. Green's theorem tells you that if you are finding this flux integral, then you can actually do this half. I don't know why this half is here. You can actually do a double integral over the region of the divergence of f. Well, what is partial f partial x? Partial f partial x is 1, and partial g partial y is also 1. So I end up with a half times 2. And the end result is the double integral over r of dA. But just like we did in the previous example, if everything else is gone and you're just doing the integral of dA, you're adding up all the little bits of area, that's the area. So this integral, if you do this line integral, you calculate the area of the region that you're walking around. So let's use it. So this is the Green's theorem area trick, basically. That the area of a region is half of the line integral of, I can't ever remember the order, minus y dx plus x dy. And the trick is that you just have to make the curve be the boundary of the region. And you have to walk around it counterclockwise. So this is not specific to this example. This is just how we can use Green's theorem to find area, which I think is listed over my head as like the third objective. So this specific integral, it just ends up like that this specific line integral randomly happens to calculate the area of a region. Okay, so in this case, instead of using Green's theorem to get out of calculating a line integral, instead this time we're using Green's theorem to get out of calculating a double integral. We're saying, oh, well, I know what double integral I want to calculate it. I'll do a line integral instead. So let's do this line integral. To do a line integral, you need to parameterize the boundary. Like you need to parameterize the curve. So here's our ellipse. It goes from minus a to a in the x direction and minus b to b in the y direction. And our easiest parameterization for an ellipse is letting r of t be a cosine t, b sine t. And we'll go from 0 to 2 pi. Now, it's very easy to get lost in the notation here. When you declare a parameterization, what you've done is you've decided what x is, and you've decided what y is. And so if anyone ever refers to x or y in your line integral, which here they are, they're all over the place, this is x and this is y. So in particular, like here's a dx, right? Well, if you know x, what's dx? The answer is you've practiced this forever every time you do substitutions. If x equals a cosine t, you can find dx. You take the derivative. And hopefully you've been trained to actually have the dt here at the end. Otherwise, none of this makes any sense. Similarly, if you know y, you can find dy. You take the derivative, and you need a dt. So when we're finding this area, I've now turned the line integral into a t integral of minus y dx. So here's minus y dx I don't know why I thought I needed to write a random dt, plus x dy, plus here's x dy. It looks like I have ab sine squared t plus ab cosine squared t, and they both have a dt. If I factor out the ab, then I get sine squared t plus cosine squared t. What's sine squared t plus cosine squared t? That's 1. So this integral is just 2 pi. The 2's cancel, and I get my answer for the area of an ellipse. Does this seem reasonable? Yeah, it seems reasonable. If it was a circle, then a and b would both be called r. So then I would get that the area of the ellipse was pi r squared. So that seems good. Anyway, the point of this is if you ever need to find the area of a region, and it turns out that the region is hard to deal with, but the outside of the region is easy to deal with, then you can be like, yeah, I don't want to do the area with a double integral. Instead, I'll do the area with a line integral. And you do that if the line integral is easier. In this case, it was.